That's my slide. Okay. All right. Okay. Check. All right, can you see the slides on the screen? All right, good, thank you. All right, let's continue with thermal evaporation. Yeah, not only thermal evaporation, thermal and electron beam evaporation. So as we discussed last time, evaporation is one process that falls under PVD. Okay, evaporation is one process that falls under PVD or physical vapor deposition. Okay, in PVD we have evaporation, we have sputtering, and evaporation can be divided into thermal evaporation, can be divided into electron beam evaporation. And for sputtering, we can divide it into DC sputtering, direct current sputtering, and RF sputtering, radio frequency sputtering. So let's just go through evaporation first. Right. So this box that you can see here is actually the chamber. Okay, chamber space that you have in order to run evaporation process. Okay, so this whole box is actually the chamber. Okay, to host the process, to run the process. So the chamber is connected to vacuum pumps, bawahnya vacuum pumps, so that you can pump down the chamber down to the required vacuum level, for example, 10 to the minus 5, depending on the requirement of the process. Okay, so connected to the vacuum pump, and then you have your source here, down here. Okay, for example, we discussed last time that we can evaporate many different materials, for example, metals. Okay, normally untuk evaporation kita pakai untuk evaporate metals, but not just metals, but commonly used for metals. For example, silver, aluminium, copper, okay, AgAlCu. Typically those with melting points of lower than 1000 degrees Celsius. Typically, they melt lower than 1000 degrees C. Let me just prove your friends. Okay, all right. So typically with melting point of less than 1000 degrees Celsius, commonly metals, right? So you put your metal into a crucible ataupun tungsten boat. Okay, has anyone done any evaporation last time during your FYP? Adakah yang pakai evaporation system? Has anyone evaporated anything? Ada pakai evaporate metal ke? Tak ada. Okay, so you need to put your source down there, your precursor material or source. Precursor material means the material that you want to work on, right? Okay, so at the bottom, so that will be your source, and then the H there, the distance, the vertical distance is the separation distance between your source to be evaporated and the substrate. Okay, so the substrate stays up there. So it can either be silicon wafer, it can also be glass substrate, it can also be plastic substrate, it can also be some other materials. Okay, some other materials. And depending on the system, you may have temperature control for the sauce. So that means you can actually vary the sauce temperature. You can also run at, say, for example, 200 degrees Celsius, 300 degrees Celsius. You can control the temperature, and you can also control the temperature of the substrate. Okay. Kalau you punya system tu is very minimum, then you can only run you don't have the temperature control, but just have that at room temperature. Okay. So you can with the temperature control, you can actually control or tailor the properties of the materials to be evaporated. Okay, separation distance, kalau you pernah masuk dalam no lab, sputtering room sebelah control room tu. If you open the door, then sputtering will be on the left. You go straight sampai hujung depan sekali, dekat tingkap tu ada evaporation system. Okay, thermal evaporation system. It's very old one, but still working. Okay, so we use that thermal evaporation system to evaporate metals like silver, aluminium, copper, and whatnot. So H will be the separation distance. Then you will need to pass through current through the material to be evaporated, and then it will be melted and evaporated. So producing evaporation flux. So dia akan naik ke atas, material akan fly off to the substrate. Dia akan naik ke atas. And then evaporation, you can see here, evaporant is the evaporated material, travels along a line of sight. Line of sight ni maksudnya bila you evaporate, bila you deposit, it will just go one way. Satu arah je, dia tak ada macam pergi kiri kanan. It's just line of sight. Maknanya apa yang dia nampak, dia akan just go up, right? So that's called line of sight deposition. And in this condition, you have to ensure that the mean free path of the evaporant or the evaporated material exceeds the separation distance. Okay, mean free path. So if I can write down here as MFP, needs to be more than H. Okay, H ni separation distance between the two. So that means the particles, the evaporated material needs to travel longer than the separation distance to be able to arrive on the substrate. What will happen if the MFP is less than H? What do you think will happen? If your MFP is less than H, you can write down in the chat box, you can unmute yourself. Apa jadi if mean free path is less than H? Anyone? Zik, apa dia Zik? Zik, what will happen if your MFP is less than H? Mean free path.
Over deposition on substrate. Possible.
Sorry, saya tak dengar apa tadi.
Over deposition on substrate.
Over deposition on the substrate. Okay.
Yes.
Lagi ada jawapan lagi?
Tu je kot.
Okay, alright. Okay, other answers? What if your MFP, mean free path, is less than H? The particles can travel through a distance less than the separation distance. What will happen to the deposition? Hadi? MFP less than H. H is the separation distance. MFP is the mean free path. So that means your particle can travel up to MFP. Paling jauh dia boleh pergi MFP je. Minyak sampai situ je. Apa yang jadi? Hadi? Oh, Faris? Okay, go slow deposition. Okay. Lagi yang lain? Any other answers? You go with go slow deposition, okay? Any other answers? Lagi other answers? Leah? Sejak saya nak reply ni. Okay, masih ada minit. Okay, how about others? MFP less than H. Cuba tengok tu, dia punya diagram tu. Apa jadi? Juaria. What do you think, Juaria? MFP less than H. Mean free path of the particle, material yang kita nak evaporate tu, less than H. H is the separation distance. Mean free path is the maximum distance it can travel. Ready? Alia, anything?
Saya rasa yang kalau MFP tu lagi rendah kan, benda yang kita nak evaporate tu dia macam jadi melt sikit, jadi cair, jadi bentuknya mungkin berubah kot.
Okay, bentuk berubah. Okay, alright. Okay. Thank you. Any other? The last one before I bicara sia. Kavina. Kavina, what do you think? MFP less than H. You nak PKL dari Penang. Incomplete deposition or slower rate. Okay, you nak PKL sampai dari Penang. Keluar dari USM nak pergi KL. Minyak sampai Sungkai je. Minyak kereta sampai Sungkai je. Okay, jadi? Right. Deposition cannot happen, isn't it? So dia travel tak sampai pun. Dia travel MFP to maximum. If you go back to the definition we learned last time, is the distance traveled by the particle before the next collision. So that means that during the next collision, they akan gone and scattered into different directions and won't hit the substrate. Tak akan sampai. Okay. So worst case, deposition cannot happen at all if the MFP is much lesser than H, for example. Tak sampai lah particle sampai halfway, for example. If your separation distance is like 30 cm, satu pembaris panjang, but then your MFP is like 15 cm, for example, or maybe 1 cm, tak sampai langsung lah. There's no deposition happening and there's nothing detected on the substrate. But if you said incomplete deposition or slow rate, that can also be true if your MFP is just less than your H. Still less, but then just less. Sikit je, eh? You're talking about like 30 cm for your H and then 29.9 perhaps, or 29.8 for your MFP. Maknanya just about there, about to arrive, but not quite. And you'll probably detect when you characterize your sample dalam project, for example, you'll probably find aluminium, kalau you evaporate aluminium evaporated on the substrate, but not quite, because you'll probably find patchy or patches of aluminium on the silicon, for example. Okay, so it really depends. If you talk about this case, MFP less than H, it really depends on how much less. Kalau it's like very much less, then of course you will have nothing on your substrate at all. If your MFP is just less than H, dekat-dekat lah CP nak sampai, ataupun you apa ni balik KL kayaknya dah about right lah, sampai Jalan Duta lah, tapi tak sampai, tak masuk town ke, for example. So just there but not quite. So in that case, you may experience incomplete deposition or slow rate. Okay, so so both cases are accepted depending on the magnitude, okay, on the difference. Okay, so that's the thing. So in essence, when you set up a deposition system or when you run the deposition process, you have to make sure that the process can ensure that the MFP of the evaporated materials, sama juga dengan proses lain selepas ni, this is the very basic for all that thin film deposition. MFP of the particles in this case the precursor material by sputtering ke evaporation ke, has always always needs to be higher than the separation distance between the material and the target material or precursor material and the substrate, right? Right, there are a few process parameters involved, vacuum level, temperature, distance, blah, blah, right? So control parameters, of course, the film thickness. Kalau you want to evaporate, say, 500 nanometer, tiba-tiba we dapat 100 nanometer je at the vacuum level. Then something's wrong. You're short of 400 nanometers, so that could be due to many things. Okay, you have to look into the process parameters, the setup, the what we call the actual real-time evaporation itself. Does it really happen or tak evaporate pun sebenarnya? So the precursor material just stay there in the tungsten boat, right? Impurity concentration, defect density, and whatnot. So these are among the important things that you have to understand, right? So the very same thing here, arrival flux of atoms, F arrival, flux of arrival equals the number of evaporant atoms, which are the materials that you want to evaporate over area times time, okay? So the rate of film growth is a strong function of T of your source. So to be able to evaporate, you have to pass through in a thermal evaporation. For thermal evaporation, for E-beam is different a little bit. You need to pass through current, kat sini. You're gonna pass through current at some point. If you have done thermal evaporation before, then probably you can appreciate this better. So you turn on the current. At some point, you will see that your material duduk dalam tungsten boat. Tungsten boat macam nanti ada kot, I think in the next slide. Tungsten punya material, tapi dia ada macam for it to sit, ada lubang for it to sit. Then you connect the boat here. You'll connect the boat there. Dia bentuk macam tu lah. And you put your material in here, say aluminium wire to be evaporated. Okay. So you pass through the current kat sini. Then at some point the material will start to melt, and then it will produce liquid aluminium to be evaporated. Okay, to be evaporated sampai ke substrate ke atas, right? So it's a strong function of temperature because temperature in this case is decided or dependent on the current. Okay, the higher the current, the higher the temperature experienced by the material, and that will determine the evaporation rate and eventually the thickness that we'll get. The higher the rate of evaporation, the higher the thickness that you'll get per unit time, right? So mean free path is again average distance which the gas molecule or the evaporant, the material to be evaporated, travels before collision. Okay, travels before collision. Dah langgar, it will be scattered or gone. Okay, sebab so dia tak akan sampai kepada kita punya destination, right? So if you can see down here in the table, you can see at different levels of vacuum, we'll get different levels of MFPs, okay, mean free path. So for example, if you're operating at 10 to the power -2 torr as your vacuum level, then the MFP is only like 0.5 cm. 0.5 cm, kecil je. Mana tak boleh travel pun sampai not even a cm, right? So the naik sikit habis, gone MFP. So imagine if your separation distance is like 30 cm, satu pembaring panjang, so of course you get nothing on the substrate. On the other hand, if you operate at 10 to the power -4, your MFP is like 51 cm. So if your separation distance, your H is 30 cm, will you get any deposition in this condition? Will you get anything evaporated on the substrate? Yes or no? At 10 to the power -4, your H remains at 30 cm.
Yes.
When you get any deposition, right? You get deposition, right? Because your
Yes.
MFP is more than, okay? Because it's 51 cm, which is more than 30 cm. So you have like 21 centimeter extra lah for it to travel. Okay, sebenarnya, tapi dia dah sampai pun, okay? So that means you need to have at least 10 to the power -4 monitor vacuum level in order to ensure successful arrival of the atoms to the substrate. Kalau you evaporate 10 minus 5, it will go like 510 cm, so 5.1 meters. Dia boleh pergi 5 meter tapi nak pakai 30 cm je. Confirm sampai punya, okay? Confirm sampai. So and the same goes to others. So if you evacuate your chamber down to 10 minus 7, can go up to 51,000 centimeter. Terlebih lagi kan, melimpah-limpah. Tapi it will just hit anyway, right? So 10 minus 9, of course, you don't have to. Okay, so this basis will also be applicable to other deposition systems that we're going to discuss later on as well. So kalau you faham ni 10 minus 4, it can go up to 50 cm, 51 cm in this case, 10 minus 5, 500 cm. Then you can already design the vacuum level requirement for your own deposition system if you have to design one. Okay. Maknanya bila nak design tu vacuum level kena pakai berapa? Okay, 10 minus 5 should be okay. Then what sort of pump do we need? Then you have to go back to the rotary pump, the fusion pump, or whatever turbomolecular in order to deliver the the intended vacuum level. Okay. So say at 10 minus 5, the collision experienced by the molecule, the gas is like 90 collisions per second. Kalau 10 minus 2, like 90,000 collision per second. That will remove the evaporant from the path. So dia akan stray lah, dia akan scattered and gone and tak sampai lah. Sampai. Then you can see all other important parameters as well. Okay, when you did, siapa last time buat sputtering itu? Izati kan? Izati? Was it you? You did zinc oxide sputtering, right? Izati? Betul guys, Izati? If I remember correctly. Yeah. Did you experience, from your sharing, did you experience any thickness problem if you put the samples in the center or on the side of the plate? Dekat you be mounting tu kan dia besar kan? You put dekat center atau you put dekat ujung, ada beza tak thickness? Did you notice any difference at all from your own experience? Ke tak semua kat tengah je, kat tepi tak ada? Kat tengah je, okay, kat tengah je, then no issue lah. Because if you run this, tapi you sputter kan, tapi pretty much the same thing. It's just that sputtering ni is less line of sight, dia lebih pergi multiple direction lah, but evaporation is like one way. Okay, if you run evaporation process, okay, kalau you punya material say aluminium kat bawah ni, and then this is your silicon, for example. Silicon wafer holder, this is the place that you need to mount your silicon, the holder je. Then you say you mount your silicon wafer satu kat sini, satu kat tengah, satu kat tepi ya. If the wafer holder is too big, if it's too big, too wide, then because this process, this evaporation is a line of sight in nature. Line of sight tu maksudnya dia pergi satu hala je, dia tak, it's not that open like that. Dia tak buka macam cone tu. It just go straight. Kan dia akan just go straight. So at some point you will probably experience thickness deposited, aluminium deposited kat sini is thicker than the aluminium deposited kat ujung. Okay, because of this issue, okay, you will suffer from uniformity problem if the holder is too big and you have to put your samples too wide sampai ke ujung. So because the deposition is like line of sight nature, dia bukan macam not like that, not like that, not like that. It just goes straight. So yang mana yang duduk kat tengah tu will experience or will get more materials to be deposited, and as a result you get higher thickness on the center, in the center part, if you compare to the side. Okay, so this is the uniformity issue that is normally experienced by evaporation process. Right, film deposition is not uniform throughout the wafer due to difference in the distance between the source and the wafer surface. Yes, if you check the distance here, yang tegak ni right, normal to the surface, against distance here, of course distance kat tengah ni is the shorter distance, right? Kat sini lagi jauh, longer. If you go far away from the center, it's going to get longer and longer, and that will also be related to your mean free path as well. Kalau mean free path kat sini, kat tengah ni, it's a lot shorter, but if you go far away, then probably it's exceeded already, and dia tak sampai. Okay, so the angle which the flood arrive is different, so that will cause the distance traveled to be longer. And to be able to mitigate this issue, to control this problem, overcome this problem, the sample can be rotated. Okay, so holder ni, you can actually rotate. As you do, okay, kalau ni buku saya, kalau ni sample holder. So as you run the process, you can actually rotate macam ni lah. Can actually rotate. That will help a little bit, but if your sample is still at the edge, right? Cumanya dia akan help a little bit in that sense. Cumanya if your sample is just too wide, then that's not a good practice to begin with. Tapi of course, if you run rotation, that will help to improve a little bit from non-uniformity issue. Okay. So problem with evaporation is difficult to get thickness uniformity over large wafers. So in Silterra, for example, we have 8-inch 200 mm, which is already large. So if you recall our earlier lecture, we've been talking about 12-inch as well. Other fat yang run 12-inch, other fat yang run up to 18-inch, 450 mm, 45 cm wide. Just imagine, that's only one wafer. 45 cm is like pembaris panjang tambah pembaris pendek. So that will be the diameter of the wafer. A single wafer aja yang you need to run. And if you have like a big chamber and you need to run this process in batches, maksudnya your wafer will be mounted at some angle dalam satu batch. So satu batch, one wafer dah 45 cm wide. So just imagine another 45, another 45, another 45 coming together as a big plate to experience evaporation process. Just imagine the non-uniformity issue experienced by all the wafers in the same batch due to line of sight deposition. Okay. Kalau small sample macam kita buat dalam lab 1 by 1, 2 by 2 cm, okay lah, no issue. But if you talk about 45 cm single wafer in a batch, worse, right? So difficult to get thickness uniformity of large wafers. Multi-component firms require multiple sources. So if you run this process, for example, kalau you evaporate aluminium saja, then you won't have much problem because it's only a single source, and you only have to make sure that it is melted at its own melting point. For example, if you talk about aluminium, I think the melting point is somewhere about 660 degrees Celsius or so. If you talk about silver, it's like 900 plus, 930, 960 degrees Celsius. So you need to ram your current until your current is able to melt that particular material at its melting point. Okay, so it's still easy because it's only a single point. It's only a single material. Tapi kalau you nak evaporate two different materials together, for example, kalau you mix aluminium dengan silicon, aluminium melting point is like 300 plus degrees Celsius, silicon 1400. Tapi kalau you nak kalau you nak melt them together in a single boat, will they be able to be evaporated uniformly, do you think? You letak aluminium and silicon dalam satu boat, you nak evaporate them together, will you be able to get uniform film stoichiometry? Stoichiometry maknanya you punya Al dengan silicon punya fraction dalam compound tu, binary compound tu, AlSi, if you like, in this case, is uniform. Is it easy to get uniformity on the deposited material? Say this is your silicon wafer, yang you nak this is your source. Then you want to deposit this AlSi. Ni soalan high level sikit lah, just to see your understanding. You nak deposit AlSi kat sini. Al plus Si with a specific fraction. So you put ALSI kat dalam ni. AL dan SI. AL wire, SI powder. Then you pass through current. Then you want to evaporate. You think you'll be able to get uniform ALSI fraction in the film? Anyone? Any ideas to discuss on this point? Anyone? Any guess? Who said yes? Yes, we'll be able to get uniform ALSI fraction in the deposited film. Or who said no? No, we'll not be able to get that. You know, any yeses or any no's? Tengok sikit lah chat box, ada tak reply? Tak ada pun.
Saya nak tekan no.
No, okay, why no? Aziz?
Sebab doktor cakap pasal difference of melting point.
Okay.
So bagi saya tu a big problem lah untuk dapatkan apa tadi?
Fraction
Uniformity.
of uniform ALSI fraction in the film. Okay. So Haziq, what do you think? You cakap no kan? If we pass through the current through the source kat bawah ni,
Okay.
then that current is able to melt, say, some of the component kat bawah ni. What will happen? What will happen on the deposit layer? Do you think? Kalau tak dapat, then kita akan dapat apa dekat deposit layer tu? What do you think?
Kalau hanya some of the source is melted, then kita takkan dapat our target of deposition lah.
Okay, alright.
Then
Okay, okay. Okay, so
tu
kita
je.
dapat. Okay. Others, what do you think? Anyone said yes? Or anyone agrees with Haziq? No. Kalau no, okay, the answer is no. Takkan dapat. Atau at least susah nak dapat lah. Susah dapat. Kalau no, what between AL and SI, what do you think we'll get more in the deposited layer? Will you be able to get, katalah you nak dapat 50-50 lah, you targeting 50-50, 50 of AL, 50 of SI in the firm. Tapi you tak akan dapat uniform. You akan dapat one is more than the other. Which one will be more than the other? Any guess? By the logic that we discussed just now, agak-agak lah. Ni soalan application sekarang. Tapi kalau you faham ni kira okey lah. Mimi, any idea Mimi? We'll get more of one than the other. The one that melted first, good point. What do you think? Which one will melt first? Will the silicon melt first or will the aluminum melt first? AL, okay, good. AL, why AL melt first? You can see the question now. Soalan ni daripada uniformity, and then it goes to the melting, then it goes to the AL, and it goes to why AL melt first. Berangkai Kenapa AL melt first, Mimi? Yeah, perfect. No melting point. As simple as that, right? So the answer is you will not be able to get uniform ALSI of 50-50 because they have differences in melting point. AL melts at 660, I think. You can check on Google now. Tulis kat bawah ni, dan check box kalau you jumpa. AL melts at 660, I think, if I'm not wrong. Cuba cross check, tolong cross check and write in the chat box. And silicon melts at 1400. Kita discuss waktu Chokrowski dulu kan. The wafer preparation tu. Then that means the difference like 500 degrees C in melting point. So of course, if you pass the current, at some point AL will melt first. Bila AL melt first, then which one will fly first? Which one will evaporate first? AL, right? AL will evaporate first, then as a result, you'll find more of AL than silicon in the deposited layer. So you won't be able to have 50-50. Sebab dia punya melting point is different. Bila melting point is different, then the vapor pressure is also different. So, right, this is another relationship. Vapor pressure, you can check later on. Melting point dengan vapor pressure punya relationship. Vapor pressure ni is different for every single material that you want to deposit. Okay, so as a result in this particular case, kita akan, if you do characterization dekat film ni, you akan jumpa banyak AL, silicon sikit-sikit je. Bila you habis evaporation, you akan nampak, oh silicon banyak lagi tinggal kat bawah ni, kat boat ni. Sebab dia tak evaporate lagi bos, sebab kadang kita already right to evaporate aluminium, tapi tak cukup untuk evaporate apa ni, silicon. So as a result, you'll find more aluminium in the deposited layer, but more silicon left in the boat, not done, not evaporated. So that's why bila you run evaporation process, you need to use multiple sources for multiple materials. So that means instead of having one point source ni, one point, you need to have 2 point. Okay, maksudnya 1 point controls aluminium, 1 point controls silicon, and each point is controlled by different level of current. For aluminium, you need lower current level in order to melt the aluminium. For silicon, you need higher current in order to melt the silicon, so that you control knob lah, so that you eventually end up with 50 of aluminium, 50 of silicon in the film. But it cannot be done by single point. Okay, so that's the thing. So it's kind of the application side of this single point. And the third one, difficult to evaporate. High melting point sources typically is done for 1000 degrees Celsius and below. If you talk about palladium, platinum, zinc oxide, silicon nitride, silicon carbide, tak boleh evaporate. Guna thermal evaporation. But they can potentially be evaporated by electron beam evaporation that we're going to discuss later on. So electron beam, it comes with high energy, macam implant punya konsep. So it will bombard the target, melt the target, and evaporate. So dia punya mechanism between thermal dengan E-beam, dia punya source dia. Satu, kita pakai current passing through so that it melts. Done. And on the other hand, electron beam, kita pakai electron beam to bombard at high energy macam implant. Macam implant dengan diffusion lah. Satu yang soft, satu yang high energy, but then for the very same purpose. Okay. So electron beam can do more, can cover more materials because of its capability by the E-beam bombardment. But for this current by thermal evaporation, just typically 1000 degrees Celsius and below punya melting point je yang kita boleh evaporate. So if you have a high melting point sources, you can either go to E-beam evaporation, or you might want to go for sputtering or some other CVD later on. Okay. Low throughput due to UHV, this one depends. Typically kita pakai evaporation in mass production. The throughput is not that bad, because if you go back to the vacuum level, it's like 10 to the 5, 10 to minus 5, 10 to minus 4, which is not as bad as 10 minus 7 minus 8. If you're talking about minus 7 minus 8 minus 9, that would require a longer time for the pumping down, so that will cost you throughput. Okay, lagi lama nak vacuum sampai ke minus 7 minus 8 minus 9 or even lower, and that requires time, longer time. But if you talk about minus 4, minus 5, it's actually nothing for mass production. So it's not really a big deal for low throughput, because it's not UHV to begin with. Okay, kalau you need UHV, kita dah discuss itu medium rough vacuum, medium vacuum, and UHV, ultra high vacuum. So if you're not operating on UHV, then you will be okay. Poor stat coverage is the issue that we discussed before. Here, this one. If the holder is too big, but that can be mitigated by rotation, real-time rotation. Okay, advantages of the system or this process is little damage to the wafer because the energy is not that high. There's no bombardment effectively. And then deposit films are usually very pure, the UHV. Okay, one more thing, if you talk about the vacuum level, as you go down here, as you go down from 10 minus 2 to 10 minus 9, the purity of the deposited layer will increase. Maknanya, if you deposit at 10 minus 2, for example, you probably you probably have like a couple of, not a couple, you probably have some level of oxygen dalam chamber to left because it's not evacuated completely. So maknanya as a result, bila you run the evaporation, you may have some oxide of aluminium oxide, silver and oxide, whatever, copper and oxide left because the oxygen is left not effectively evacuated by the pump because you're only operating like 10-2. On the other hand, if you go down to the vacuum level ni, you go to 10-5, -6, dia punya evacuation dalam molecule tu dah evacuated, dah already sucked out. So the chamber punya purity is already very high. So as a result, the purity of the deposited layer will be very high as well. Mana pure silver, pure aluminium, pure copper. Kalau ada oksigen pun mungkin sikit-sikit lah. Tolerable level. Electron beam based probe are available for analysis of the surface structure during growth. If you run electron beam evaporation, you can actually have a probe untuk monitor in situ growth. In situ, what is in situ? In situ tak tulis kat sini . What is in situ growth? Saya dah sebut itu kan waktu 386. What is in situ growth? Can use electron beam probe for analysis of the surface structure during the growth, during the deposition. Apa maknanya in situ? Bahasa mudahnya, ya, on site, exactly. Ya, on site ataupun bahasa nak senang faham, in situ tu di situ lah, ada kat situ . Ada kat situ. So dalam the electron beam tu ada, di situ ada monitoring system to check on the crystal growth, on the film growth during the deposition. As you build on the layer, kata nak deposit 300 nanometer, as you build the 50 nanometer, 70, 80, you can actually see the real time development of the film during the growth, okay, by in situ monitoring or on site or di situ lah. Right, so step coverage is another issue. On top of the uniformity tadi, so it's partly uniformity, but then this one is more of if you have structures already, okay. Kita discuss sebelum ni, kalau you already have structures on the silicon, we have shading effect, kita discuss untuk implant kan. So if you have the like that angle, say 7 degree, or to implant so that you don't have channeling effect all the way through, nak bagi the implant at a more precise depth, but that will cause you to suffer from shading effect. Kat sini sebab dia main direct kan. So kat sini will not be covered because it's line of sight. Unidirectional. Line of sight unidirectional, single direction. Dia pergi satu arah je. So it's not like opening like cones. So as a result, if you already have features or structures on your wafers, on your substrate, some parts of the substrate will be shaded. It's called as shadowing effect ataupun shading effect. Kesan bayang. Shading effect. Some people call shadowing effect. Dua boleh Shading boleh, shadowing pun boleh. So it's due to line of sight deposition. Usually this case can be mitigated by rotation. You can rotate macam tadi, or you can forget using evaporation but instead go for sputtering or go for CVD later on. Sebab evaporation is very line of sight. Dia one way je, satu arah unidirection. But if you go for sputtering, it will be more omnidirectional. Omni means lebih banyak arah. Omnidirectional. Kalau satu je unidirectional. Kalau omnidirectional means coming from various angle. So it goes to various angle. Maknanya dia buka lah, dia punya code tu di cover, but then sample kat sini pun uniform, sini pun uniform, sini pun uniform. So that's called omnidirectional. So if you compare sputtering dengan evaporation, sputtering is more omnidirectional. If you compare CVD dengan sputtering, CVD is more omnidirectional. So kalau you tengok spectrum of omnidirectionality of deposition system, yang paling unidirectional ialah evaporation, yang tengah-tengah ialah sputtering, yang paling omnidirection ialah CVD. So if you want to get omnidirection, go for CVD. If you need unidirectional, go for evaporation. Okay, dia spectrum. Nanti kita akan belajar, lepas you belajar sputtering, you belajar CVD, then you get to see all. Tapi sekarang ni saya just explain so that you can appreciate the unidirectionality issue in this evaporation, and you can opt for sputtering or CVD to get more directionality, omnidirectionality, right? Go apa sekarang? 10.50. Let's go for another. Nak habis ni ya. Saya nak tunjuk thermal evaporation, then we stop, then we continue with E-beam in the second half. So system requirement for evaporation process, you need to have vacuum. So to be able to have vacuum, you need to have vacuum pumps, right? So you need to first define your vacuum requirement. So are you running at 10-4? Are you running at 10-5, -6, -7, and so on? So typically, if you need medium quality film, not so pure, but not too bad, you can run at -5, -6, okay? If you need very pure film quality, you need to run -9. So this requires UHV, and that requires longer time, and that will sacrifice your throughput, but that will give you a high purity layer, okay, high purity deposit layer. So it's a juggle between your throughput, your vacuum quality, vacuum requirement, film quality, and all the stuff. So it's always a juggle. There's no perfect answer to this. Right, you need cooling water because it's going to run at high temperature. So you need cooling system to cool the system down. Kalau tidak, dia akan panas. Panas dan shutdown. Dia akan ada interlock. Sistem ni biasanya kita akan ada interlock if it run at a too high temperature. Interlock ni maknanya protection system lah. If you run at a very high temperature, not protected by cooling, then it will just shut down and that's it. Equipment shut down. Sebab kalau tidak, kalau too high, tak ada protection, panas, boom. Okay, so that's why we need interlock. Nanti bila kalau you jadi equipment engineer, for example, in your career later on, you will get to know this interlock. Semua ada interlock. You nak operate robot arm, kena tekan interlock dulu, disable. Kalau tidak, dia akan ada crash macam isu yang saya cakap hari tu. There's always be interlock. You tengah run CED dalam lithography, tiba-tiba you buka pintu kotor tu. You buka pintu kotor saja, tak ada kerja kan? Tak ada kerja contoh. Tak ada, boring. Ataupun nak sabotage company ke. I don't ask you, okay. Bukan saya tak suruh. Don't do this. CD is running, scanner is running, tiba-tiba you buka pintu kotor tu. What will happen? System will interlock. Dia ada interlock, so it will just stop the spinning. Dia akan, dia tengah spin 3000 RPM, it will just stop. Habis stop. Habis wafer kena rework. If you run CD. If you run Edge, just imagine what happened. Scrap. Right? So we learn about rework, we learn about scrap. So interlock is here to protect the system. Tapi kalau you buka waktu tengah run, that means you'll probably be fired if you did that on purpose. Mechanical shutter, you can actually run this shutter bila you run evaporation. Contoh, you ada sauce, you ada wafer. Then you will normally have shutter in between. Shutter ni macam, okay, kata ni saya beli buku. Okay, you ada sauce kat bawah, you ada wafer kat atas. Ni shutter. Shutter ni dia akan, bila you start running the evaporation process, sputtering pun sama. Bila you start running, you start passing through the current and it will start to evaporate. The moment it just started, the purity of the film is not good yet because it just started. So at that point, whatever you evaporate, you don't want to get them to be deposited on the silicon substrate just yet because yang awal-awal tu dia belum high quality lagi. So at that point, you want to block the deposition. You want to block the path. Maknanya you tutup jalan lah. Tutup jalan daripada it gets to be deposited on the silicon. So kita ada shutter. Shutter ni dia akan, the moment it runs for like few seconds, it's okay already. I don't remember the second, 15, 30 seconds or so. Then you start opening the shutter. Maknanya dalam chamber tu you buka shutter. You buka pathway lah, macam you buka gate untuk dia masuk. Then the path will be open for deposition. Sebelum tu, whatever deposition yang just started tu will just be deposited on the shutter. Dia tak sampai sebab you block kan, dia line of sight kan, one direction. So just get deposited on the shutter, but it's not affecting the substrate at all. So the moment it's already pure, after a few seconds of evaporation, you just open the gate, it will just go through and get deposited. So that's the role of shutter. Okay. Right, electrical power, of course, you need to apply high current or high voltage, depending on what system you're running. So if you talk about evaporation, you have two systems. Thermal evaporation is also called resistive heating. Meaning you pass through the current, change the resistance, and then melt the precursor material and start the evaporation. On the other hand, the second one is the very same thing as far as the chamber punya configuration is concerned. It's just that instead of passing through current, you use electron beam to heat the precursor material to enable or to kickstart the evaporation process. Right, a configuration of thermal evaporation system. So this is the real system. So this is the chamber yang kita duk lukis tadi tu, square tu. So this is the glass window for you to see what's going on. So you nampak gambar ni through this glass window. Okay, as the current develops, so you can pass through current through this current. Bila you nampak dia start turning to be yellow tu, nanti saya cari video on YouTube, you can also find yourself. Bila start current tu dah sampai ke certain level, dia akan jadi kuning. Maksudnya current passing through now. Kalau you turn on the knob at high current gradually, tapi you tengok dia tak ada kuning pun, dia just hitam, macam tak ada apa-apa berlaku. So that means the contact kat sini dan contact ni. Sebab dia just macam you letak tungsten bolt, ni tungsten bolt kat tengah ni. So you ada material dalam ni. So you just lock screw je. Lock screw, kemudian kalau dah habis unlock lah. You lock screw, bagi dia ketat, so that bila you pass current, it will just contact properly. Kalau memang you tak lock properly, then there's no electrical contact. Current pass through, dia tak akan masuk dalam tungsten bolt, and there will not be any yellow color at all. Okay, and you get to see this through the glass window. So yang kat tepi ni is the mounting that you have, sample mounting that you actually mount here. Bentuk macam a bit dome shape, right? So you can see bulat-bulat ni semua sample holder. So you hold the sample at various angles, you see, like that, like that, like that, like that. But you don't want the angle to be too steep because the flux will be coming at an angle, right? High angle, and that will of course affect your uniformity. And if you have features already existing on the wafer, and of course that will be shadowing effect and all those stuff that we discussed on the previous slides. So these are all the electrical control panel, turn on current or whatever. Right, okay, tungsten bolt, right, 1800 ni, you can run up to this, especially if you operate on E-beam. So tungsten bolt, tantalum or molybdenum are used as the evaporation source. Okay, filament current 200 amps ni kalau yang very high, ada IR radiation, you can see the color, right? You can see this kind of radiation as well, right? So yeah, radiation, tapi it's just minimal. Typical DAP rate, deposition rate, ataupun normally we call it as DAP rate, 1 to 20 angstrom per second. So that's like 2 nanometer per minute, 2 nanometer per second if you like. It's about 1 nanometer is 10 angstrom. Okay. Common evaporator materials, that's gold, silver, aluminium, tin, blah, blah, blah. And you can also evaporate compounds. Ni tungsten bolt yang saya tunjuk tadi. For finish, ni tungsten bolt yang tadi saya tunjuk. So if you put this on, ni dia punya holder tu. So just imagine this tungsten bolt. If I take this, so you akan isi aluminium dalam ni. So you akan mount kat sini. Right, so you akan mount dan screw kiri kanan tu. Then you akan letak aluminium kat dalam. So in this case, you have like a couple, right? You have 1, 2, 3, 1, 2, 3, 4. Okay, 4 lah. You have 4. So you can do multiple control. So kalau you ada like 4 different points, then you need to control by 4 different levels of current. Okay. So satu ni satu current ya. So it can also look like this for small one. It can also be like macam perahu tu. You boleh letak wire dalam ni, and to be evaporated, you can mount on this side, screw kiri kanan. It can also be like that, macam kolam sikit so like that. So you can put all the stuff in there. Okay, ni dia punya schematic lah, example of different tungsten bolt punya design. So it can be like that dimple, it can be like that dimple, hairpin, blah blah blah. Banyak design you can watch the video later on. I've put here already. Yes. Right. Any questions so far? Thermal evaporation?
Nak tanya doktor pasal mechanical shutter tadi.
Yeah.
Kalau macam mana tak ada possibility untuk ada deposition dekat mechanical shutter tu ke?
Yes, ada
Sebabkan dia
ada possibility sebab okay. Kalau you tengok dekat diagram, bukan diagram, gambar on the left ni. Shutter ni okay, you mount the dome here, the sample punya dome, sample punya holder, then you have your shutter here. You want to deposit early evaporants, early flux on the shutter. Memang you nak deposit on the shutter pun.
oh,
Sebab shutter tu supposed block. So kata dia punya point kat sini. So due to line of sight, it's coming like that. It's coming like that. It may be a bit of cone lah, a bit of cone, tapi it's not too wide. And you want to block all this during the early deposition. So that means bila you just turn on the current, the early material yang you evaporate to is not of high quality yet. And you don't want that to be deposited on the silicon ke glass kat atas tu. Sebab dia punya quality tak bagus lagi. So you need like a couple seconds to wait before you actually remove the shutter and let it fly through the path. Okay. So bila awal-awal, bila shutter is still there blocking the path, memang you nak evaporated material tu block deposit kat shutter pun. Sebab dia akan block. Sebab evaporation dah berlaku. Tapi you tak nak sampai kat ujung. You tak nak sampai kat belakang ni. Sebab dia tak bagus, quality is not good yet. So you block first. You intentionally block. Bila you intentionally block, of course the deposited material will be deposited on the shutter. Sebab dia nak pergi mana lagi kan? Dia boleh pergi kat situ je kan? Dia tak boleh pergi tempat lain. Dia hanya pergi depan atas je. Dengan maybe some opening. So it'll just be deposited on the shutter. And that is intentional. That is what you want to do. Bukan you want to avoid. So after some time, bila usually dia ada recipe lah. After some time, after few seconds, shutter will be automatically open. You akan remove shutter tak tepi. Macam ni Kalau dalam lab kita remove manually je, kita guna knob untuk remove gerakkan dia. Tapi kalau dalam recipe, dalam production, it will just be defined in the recipe. After certain seconds, shutter open. Open means dia akan clear from the path, then the deposition will run. And at that point, bila you dah start the deposition, okay, saya lupa sebut satu benda tadi. Dekat sini, dekat tengah ni, dia akan ada crystal monitor to detect the deposition rate. I think Izzati, you probably can appreciate this during your sputtering hari tu, ada crystal monitor to measure the deposition rate. So at that point, you can actually see how many angstrom per second is being deposited on the substrate. Sebab you monitor kat tengah ni, macam letak tepi sikit lah, sebab you tak nak dia block kan. Tapi that will actually read the real-time deposition rate that you are actually depositing now. Daripada situ you can, bila you dah dapat angstrom per second from the sensor, crystal monitor tu is a sensor lah technically. Bila you dah dapat the value, you can then plan your deposition time. Sebab bila you dah tahu berapa angstrom per second, then you know for 100 angstrom, how long do you need? You boleh buat the calculation lah. You can plan the deposition time. Dia akan in fact tell you the current thickness pun. For example, as you go during the process, you probably see now it's like 23 angstrom is being deposited. Ataupun 2.3 nanometer lah. Okay, so that will develop over time, that will increase over time. So you can get to see when do you need to stop. If you run the system manually, kalau dalam mass production, it's all defined in the recipe already. How long does it run? Shutter buka open lama, sekali shutter tutup balik. Then current akan drop. Semua dah define dalam recipe. You just press on je, semua dah run. Dia akan run by steps. Okay, macam Lito punya recipe juga. Mungkin ada 10 or 11 steps. So the very same thing goes on for this particular process as well. You define everything in the recipe. Then the moment you run the process, the recipe will just run step by step daripada mula sampai habis. Then bila habis shutter akan close, tutup balik, current akan drop. Then you don't see any more yellow color sebab dah deposition dah stop. Then you can vent the chamber up to atmospheric level, blah blah, then unload the sample, then done. Process done. Okay. So any other question before we stop? 11.04. All good? Semua faham? Thermal evaporation. It's quite clear, right? Cool. So now it's 11:04. Kita break about 10 minutes. So I'll see you again 11:15. Okay? Lebih kurang, eh? Right then. See ya 11:15 inshallah. Bye-bye. All right, let's continue. Okay, can you see the slides on the screen? All right, good. So electron beam evaporation is the second type of evaporation we discussed just now on thermal. So the main difference between thermal and electron beam is the source. Okay, the thermal uses current supply to initiate the evaporation process, while electron beam uses electron beam, okay, at high energy to bombard on the precursor material so that you can kickstart the evaporation process. So it's more complex, extremely versatile because it's capable of evaporating higher melting point materials. Okay, if you compare to thermal evaporation, it is typically up to 1000 degrees Celsius melting point. You can push, but then you need a very high current to initiate evaporation. So that's why the common materials are with melting points of lower than 1000 degrees Celsius. So electron beam can achieve temperatures in excess of 3000 degrees Celsius. So that's like 2000 more. Use evaporation cones, crucibles in a copper hearth. Typical emission voltage is like in the range of 8 to 10 kilovolts. Exposes substrate to secondary electron radiation. X-rays can also be generated by high energy beam. So X-ray will also be generated during the process. Low level X-ray, but then it's there. Typical deposition rate are in the range of 10 to 100 angstroms per second. It's much higher than thermal evaporation because of the nature of the bombardment. Common evaporative materials, everything a resistance heated evaporator will accommodate plus. So all the materials can be done on electron beam, but not all can be done on thermal evaporation. Okay. Yang material yang melting point rendah pun electron beam can handle. Yang tinggi pun dia boleh handle, but thermal can only handle the low melting point ones, right? So common are nickel, platinum, iridium, ruthenium, titanium, vanadium, zirconium, blah blah blah. Aluminum oxide, RTO, zirconium oxide, tin oxide, all the oxide, carbide, nitride, banyak benda yang boleh buat. So it's more flexible in that sense. Okay, evaporation, electron beam evaporation, it may look the same, so that's why saya pakai yang sama. But then the mechanism is different. The mechanism inside is different. So for example, in this case, you can see this is the electron beam punya source, E-beam. So that's the beam generated. So then it will be deflected at 270 degree and then hitting the materials here. Say if you have ITO to be evaporated. So this is your chamber. So this will be your sample holder. Okay. So you have the very same directionality nature like thermal evaporation. It's just that the source is different, like from beam in this case. Okay, so you can see that this is the the cathode, the filament, 10,000 kV to generate the beam. So beam will be generated. So this will be the beam. Magnetic field is there to bend the beam at 270 degree. And then, yep, these are the pockets of the evaporation materials, right? So you can actually align the beam to the pocket that you want to evaporate. It's a cooling water can others, but they are high kV, high current system. So then everything is contained within your chamber. Okay, chamber sini ya. timber. Right? So then you may have your ITO or something here. ITO, for example. Then you may have, like, I don't know, silicon nitride, perhaps. 270-degree band beam electron gun is most preferred. Filament is out of correct direct exposure from the flux, so you can use magnetic field for the beam positioning. Band to pakai magnetic flux, magnetic field. Sorry. Additional electrical field can also be used to produce a sweep, XY sweep. It can also be done. That's another feature. So this is all the processing, the mechanism involved. Multiple pocket can also be done if you have more than one material to be evaporated. For example, if you have compound material like kalau solar cell, there's research that uses ZAT487 solar cell, for example, copper, zinc, tin, sulfide. Okay, so copper, zinc, tin, sulfide. So you can either use 4 pockets, or you can also use 3 pockets. For example, copper, zinc, tin. So that means copper, zinc, tin. Pakai 3 je pocket, but then you use sulfurization process dalam furnace as your next step. It can also be done like that. Sulfurization, passing through sulfur lah. So that you eventually end up with CZTS, because as CZTS solar cell. So copper, zinc, tin, sulfide, right? So perovskite solar cell pun boleh buat macam ni. Depending on the precursor material that you want to use for your process. So electron beam evaporation videos here you can watch later on. So resistive heating versus electron beam heating. So resistive is thermal. Yang belah kiri thermal, yang belah kanan electron beam. Thermal we also call it as resistive heating. Sama. Resistance heating, resistive heating sama je. Right, so that's the difference in the schematic. You can see this one involves electron beam. This one is just heating process by passing through current. Little resistive heating. But others are pretty much the same. Yeah, done. We're done with evaporation. So we'll continue with sputtering process. Sputtering is another process. This bit. Right, sputtering is the second type of PVD process. Remember, bila you sebut deposition, thin film deposition, you always have to come to the B category first. PVD, CVD. Physical vapor deposition, chemical vapor deposition. And under PVD, you have evaporation, you have sputtering. And evaporation ada dua, thermal and E-beam. Sputtering, you have DC, you have RF. Okay? CVD lagi banyak. Lagi banyak dia punya kategori. So sputtering is a process in which surface particles, atomic or molecular, are physically knocked off or ejected or dislodged. Banyak perkataan yang you can use. Physically knocked off, macam kita tendang keluar. Ejected or dislodged from a source target. Ataupun kita panggil target material. Ataupun target, sputter target lah kita panggil sputter target. By using energetic gaseous ions in a plasma. So the basic here is physically knocked off or ejected or dislodgement, if you like. So we use sputter target as the precursor punya material. Kalau evaporation you ada letak powder or wire dalam boat kan, you potong kecil-kecil. But this one you use target. Target tu bentuk dia. Pernah tengok sputter target? Izati pernah tengok kan? Izati? Zinc oxide sputter target. It's round shape. 3 inch or 4 inch, I couldn't remember. I think 3 or 4 inch, right? 3 inch if I'm not mistaken. Izati dah pernah tengok. Bulat macam wafer, but then it's like 3 or 4 inch. I couldn't remember exactly. 3 inch or 4 inch, Izati? Can you recall? 2 inch wafer, 3 inch. 3 inch, right? I think it's 3. I think it's 3. Betul ke? Please confirm, Izati, if you can recall. It's 3-inch in diameter. Dia macam plate macam this lah, macam this. But then it's quite thick. So that is the sputter target that you're going to use. If you want to deposit silicon, for example, by sputtering, then you need to use silicon sputter target. If you want to deposit ITO, then ITO sputter target, zinc oxide sputter target, silicon nitride sputter target, aluminium sputter target, silver sputter target, copper and whatnot, right? So you punya material tu instead of powder or small wire, it comes in a form of sputter target. So to be able to dislodge or knock off the atoms or molecules or whatever from the target, you have to use plasma, right? So this is called a PVD process, another process of PVD. So if you look at the chamber sama, square shape chamber. So you have your argon gas coming into the chamber before we form the plasma, because argon will form plasma eventually. Ar plus ion, so you're gonna have cloud of Ar plus as a plasma, okay, forming the plasma. So dalam ni is just like the yellow thing, cloud, plasma lah tu eh. And then the chamber and then the pump is connected to the the piping, the line here is connected to the pump in order to create the vacuum level. It's typically evacuated down to 10-5, and then that is called as base pressure. So you can pump down sampai 10-5. So the moment you reach 10-5, you will inject argon with a few SCCM, 5 SCCM, 10 SCCM, depending on the process requirement. And then it will start generating the plasma by this supply. And then the moment you have your argon injected into the chamber, that will bring the pressure up to around 10-3 millitorr, selanjutnya dalam millitorr. Right? So 10-6 bar, you dah masuk gas, then they will increase the overall pressure of the chamber. So that will create plasma, and then the plasma will actually, this is target material, say this is ITO that you want to deposit. So this is your silicon, contoh. So you can also have, in this case, you have your sample down here. Okay, you have a sample down there. Right. You can also have your target mounted different way. You boleh letak bawah, letak atas, depending on the sputtering punya configuration. Sample duduk atas boleh. You have your shutter in between, shutter macam tadi, in between to control the opening. So did you control shutter last time, Izati? Ada control ke Izati shutter? Do you control yourself? Or ataupun you tak pakai shutter langsung? Can recall? Izati buat dengan siapa lo FYP? Who's your partner? Akilah. Saya nak panggil Akilah pula. Panggil Izati ya. Akilah, do you use the shutter? Ada pakai shutter tak? Can you just tembak je? Do you use the shutter? Or are you aware of shutter punya presence in the system? Gelap je, dia ada gelap. Tak aware. Senyap itu. But anyway, right, the plasma, high energy ions, Ar plus, will actually knock the atoms off the sputter target. Dia macam you pernah main pool kan? Main pool. Main pool, you target bola kan? Bola target pun pecah kan? Macam you, you pecahkan dia punya tu, bila you start main tu. So you pecah tu the atom, it's like atom dislodgement thing. Right? You target dia, then you pecah pum. So dia akan distributed. So that's sputtering, pretty much. Okay. So nanti you tengok video tu, then you can imagine. Right? Right, sputtering, it involves momentum transfer from the incident atom to the surface atom in the target material. So the momentum comes from the plasma itself, plasma to high energy ions. You can even accelerate the ions. Okay, we can even accelerate the ion. For example, if you go back here, last time when I was in Fuji Electric R&D, are you aware that your hard disk, ada hard disk drive tak? HDD, ada hard disk drive kan? Nak backup or whatever. You pakai hard disk drive tu. So the process that is used to create magnetic layer dekat dalam HDD tu, kalau ada hard disk drive yang dah rosak, you just buka je. Opak buka, tengok dia punya disk tu, dalam disk tu. Ambil disk tu is either made of glass ataupun aluminium. So when I was in the R&D team last time, to be able to create the layer untuk kita store data tu, berapa megabyte lah, berapa mana ada megabyte, terabyte or gigabyte for example minimum. So you have to sputter 20 plus of magnetic layers. 20 plus, very thin one, like puluh-puluh nanometer je every layer, but very thin, multiple layers, like 20 layers or so. So these magnetic layers yang akan store the data, okay? Akan store the data. So you get to save your whatever file, thesis, project, lab report, pictures, semua save kat tu HDD. You boleh study HDD punya operation. So the hard disk drive tu is prepared. The disk is prepared by sputtering process. Okay. So in Fuji Electric last time we use a system that we call a very big system. We call it Intervac. Intervac punya supplier. Intervac sputtering. Intervac sputtering system. It's a very big system. If you compare to CED system yang saya tunjuk gambar last time in lithography, it's about that long. Tapi dia ada dua chamber. When I was in Fuji, it was like dua layer of chamber. Ada chamber bawah, ada chamber atas, and you have like 20 different chambers running in series. Maknanya layer 1 is sputter dekat chamber 1, then these two masuk sputter dekat chamber 1, dan keluar buka pintu kedua, masuk sputter chamber 2, sputter layer number 2 pula, habis tutup robot arm bawa sputter chamber number 3, sputter. So you're gonna build like this layer, then that layer, then that layer, that layer, that layer, all together like 20 plus. So magnetic layers that are responsible to store your data. Okay, you can check later on. You can check technology ni. Technology ini is called permanent magnetic recording, PMR technology. So when I was in Fuji Electric last time, we did R&D of this technology, permanent magnetic recording. Itulah yang kita nak pakai tu, HDD tu. It's called PMR technology, bukan PMR exam tu, PT3 sekarang. Permanent magnetic recording. So you store your data in column dalam every bit. So dalam, kalau tengok dekat atas morphology SEM, you akan nampak every bit tu, dia akan store data. So that's how you get your data stored, right? So to appreciate the technology that you use day in day out untuk transfer data, whatever, takut apa computer crash kan. So that's the very thing. And the process is in the sputtering. So you pakai all the sputtering process untuk 19 layer tu. Kemudian the final process will be CVD of carbon. Dia akan cap all the layers. Sebelum tu semua magnetic layer pakai iron, Fe, pakai cobalt, pakai ruthenium, pakai all those ferro punya magnetic materials. Okay. FeCO, Ru, Ti. You can check all the magnetic punya material. Ada magnetic punya komponen kan. So semua sputtered, right? So this is the same process. Kalau you kerja WD yang buat ni, ataupun dulu Seagate atau Fuji Electric yang ada magnetic punya team. So I was in Mag team last time. We call it Mag team. Actually the magnetic sputtering lah. So this is the very process that we use in order to prepare your HDD. Okay, hard disk drive. Dia punya competitor is SSD lah, solid state drive. Okay, so nanti we're gonna have your group presentation where you have to present how SSD is fabricated. Okay, there'll be one group which will be lucky to present SSD using the very processes that we learned in order to do the fabrication of SSD. So involve momentum transfer from the plasma at energy lower than binding energy, blah blah. Reflection of a bombarding species. It can also be conducted at high energy, more than 10 keV. Impinging particle to be embedded in the target. Okay, you can, well, at some point you may also embed particles into the target, but this is not happening because you want to dislodge the atoms away ataupun knock them off from the target. Okay, bila you use sputter target tu, sputter target ni bulat kalau tengok dari atas bulat macam tu. Kalau tengok dari tepi, bentuk dia macam disk lah, right? Over time, bila dah banyak sputter ni dia main multiple ni by the plasma. Over time, you will be left with a very thin sputter target. Sebab dia dah makan. Dia dah etch away, macam etching lah. It remove, but that is not called etching. Tapi kita boleh panggil juga dalam certain condition, we call it as sputter etch. So you sputter, but then you actually etching. But that is not etching literally that we learn in anisotropic, isotropic, dry, wet, all those stuff. Tapi it's actually etching lah, as long as you remove something, it's actually like etching. Okay, but we call that as sputtering. Okay, over time you will get thinner and thinner and thinner. If it gets thin enough, then kita kena beli sputter target yang baru lah. Kalau tidak dia akan jadi brittle. Okay, because it's too thin to. Okay, you can watch this later on. Sputter video. Threshold energy for sputtering. So your system needs to run with a minimum energy in order to enable sputtering. If the energy is not, minimum energy is not met, there will not be any sputtering. So atoms will not be knocked off the target, right? So you can use this equation if there's calculation, right? The energy transfer is given by 4 times m1 m2 over m1 plus m2 squared, where m1 m2 are the mass of sputtering ion and sputtered material respectively. Ion punya mass, material punya mass. If you put them together, you get the energy transfer punya parameter. Okay. So the energy transfer reaches a maximum when m1 equals to m2. You can put that into equation and test for yourself. Sputtering yield. Number of atoms sputtered from the surface per incident particle. So for every single particle hitting the target material, there will be a number of atoms sputtered, number of atoms dislodged, number of atoms removed, knocked off, right? So macam konsep last time we measure EQE solar cell kan, satu incident photon dapat create berapa electron hole pair. So in this case, it's called sputtering yield S, and that's measured by number of sputtered atoms dislodged over number of incident ion. So untuk satu ion, berapa atom you manage to dislodge. So the more atoms you manage to dislodge or knock off, the yield will be higher. Okay, sputter yield will be higher, S will be higher. Kalau you punya atom yang knocked off is not that high, then the sputter yield will be lower. As a result, your depth rate will be lower as well. And then within the same duration, you'll end up with thin or thinner material. Factors affecting sputtering yield: mass of mass of target, mass of gas, mass of the target, as we discussed previously, m1, m2, ion energy, the AR plus. Okay, angle between the surface normal of the target and the velocity vector of the ion. Okay, the heating punya mechanism, the heating mechanism. If you talk about this chamber, for example, okay, the ion are plus kan, ion plus, AR plus. So one way to increase the depth rate ataupun the yield is by, instead of grounding the target, you can also apply negative bias. We call that negative bias. Negative bias to the target. So what will happen if you apply a negative voltage to the sputter target? What will happen to the plasma? Ataupun what will happen to the sputtering yield? What do you think? Say you are applying negative 200 volts or negative 100 volts to the target. Cuba tengok ion tu positif kan? Ion positive. And then you're applying negative bias to the target. what will happen to the sputtering process by the basic, by the logic. Ion pergi ke target, yes. Ion pergi target, so jadi apa? Sakinah. Ion pergi target. Okay, kenapa ion pergi ke target? Sakinah, you can unmute yourself if you want to.
Ion tu dia pergi dekat target
Okay, sebab apa
sebab
dia pergi ke target?
dia attracted oleh ion
Yes.
positif
Right.
target
Okay,
tu
okay. Then,
dan sputtering tak jadi.
sputtering apa? Sorry?
Sputtering tak jadi.
Tak jadi ke makin jadi?
Eh?
Kenapa sputtering tak jadi cakap?
Sekejap. Okay, sekejap saya
Okay, lagi
confused.
Okay, kejap. Okay. Let's get to the basic. Do we want the ions to go to the target?
Nak.
Nak kan? So that you can have sputtering. So that you can have sputtering, right?
Yes.
Kalau ion tak pergi kat target, will there be any sputtering?
Yes.
Okay, hold on. Okay, we use ion to sputter, right?
Yeah.
So we want ions to go to the target, right?
Yes.
Okay. If the ions do not go to the target, do we have sputtering?
Oh no.
No. Right. Okay. No. If ions are not going to the target, we don't have sputtering. When you apply bias, negative bias, do we have more ions going to the target?
Yes, more ions.
So do we have more sputtering?
Yes.
That's the thing. So kita nak ion pergi kat target kan? So bila you apply negative bias, more positive ions, AR plus, will be accelerated to the target. Maknanya apa jadi? Untuk kita dapat sputter, kita nak ion tu hentam kan? Sampai dia terkeluar. Keluar. Bila yang tu dalam keadaan tak ada bias. Bila you apply bias, the attraction will be stronger, right? Boom, lagi kuat. Bila lagi kuat, atom punya dislodgement lagi banyak ke lagi sikit? Bila langgar lagi kuat, lagi kemik ke lagi kurang kemik? Kancil langgar kancil dengan lori langgar kancil. Contoh. Kancil langgar kancil tak ada bias. Lori kontena panjang, 30 tayar contoh. Langgar kancil, lagi kemik ke tak? So that's with bias. Lagi kemik kan? Boom. Langgar terkeluar, lagi kemik. So you have more dislodgement of atom. As a result, you're going to have this. Sputtering yield for the same number of incident ion, you're going to have more atoms sputtered, more atom dislodged, more atom knocked off. Terkeluar, kita nak atom tu knock off, baru you have sputtering kan. Bila you sputter tu, you actually removing atom daripada target. Kita nak langgar dengan, kita guna ion as a medium to langgar, to collide, to bombard, if you like. So bila you apply bias, dia akan langgar lagi kuat due to the attraction that you said now. Negative bias attract positive ion. Negative positive yang basic kan. Langgar lagi kuat. So more ion will be accelerated to the target, hitting off more atoms. So for every ion yang sama, AR plus sama, dia akan langgar with higher energy. Dia bawa energy dengan dia lagi banyak. Boom, keluar lagi banyak. Boom, keluar lagi banyak. So as a result, the number of sputtered atoms will be more for a unit ion with bias. So this is what we did last time when we developed the HDD technology. During my time we developed I think 1 terabyte. Sekarang 1 terabyte is nothing, right? Kita ada more than 1 terabyte. I think what's the highest terabyte now for HDD? Anyone? We have 3, 4 in the market. Kat kedai komputer ada berapa terabyte sekarang? Do you see 3, 4 terabyte? Or 2 at least? I think more than 1, right? So that's the very thing that we did. So bias is one of the parameters that we use to optimize that process so that you end up with higher storage per unit disk, per disk. Maksudnya satu HDD tu you can produce, say previously you can only go up to 980 gigabyte, sekarang dah boleh buat 1 terabyte for example. when you do this bias kind of thing, because ada banyaklah parameter yang you have to monitor, but this one of the main parameters that we used last time, negative bias, in order to do the improvement during the R&D of HDD punya teknologi, right? PMR. So kalau you sekarang ni Fuji Electric R&D HDD dah shut down, no business, sebab dia kena compete dengan SSD by microns. Okay, you tengok micron hiring kan, so SSD is gaining traction now, harga pun dah lagi murah. And I think kalau you beli laptop, you can see laptop yang ada HDD plus SSD kan. Kalau SSD saja lagi mahal kan. You can check that on the market. Kalau HDD saja kurang lagi murah sikit, but then it's not as it's cheaper than SSD. Ada juga yang hybrid like 500 of SSD and 500 of HDD for example. Itu mahal sikit. Kalau completely SSD memang lagi mahal. So that's the thing that we have in the market, but it goes back to this process, sputtering. Okay, but then it's just on the inside of the process. Okay, okay, let me just go through one more page, I think, then we stop. It's almost 12. Right, sputtering yield. If you have higher ion energy, the sputtering yield increases. So you can induce this high energy by supplying negative bias. Sebab tadi kan Sakina cakap attraction, negative belakang, tarik AR plus, boom. Okay, ion energy is higher per unit for every single ion. It carries a bigger amount of energy. So dia akan langgar with greater impact. Therefore, you dislodge or knock off more atoms per unit ion. Hence, higher sputter yield. So up to a few tens of keV before ion implantation occurs. Well, at some point, you tengok kat sini ion implantation. When you talk about sputtering, at some point, there'll probably be some ion implantation as well if the energy is too high. Maknanya bila at some point, kalau I don't know how to explain, kalau dia langgar at too high energy, maknanya dia mungkin I don't know, the transfer is not as effective perhaps. Dia just implanted masuk dalam target je, tak keluar pun. Maknanya dia just ni tapi dia tak keluar. Mungkin ada energy transfer dalam target itself, but then it doesn't dislodge the atom. So the target itself got implanted. So mass of target, if you have higher mass of target, the sputter yield drops. Okay, you can go back to the equation and now the energy transfer. And sputtering system. Okay. Saya stop kat sini ya. Sputtering system, okay, gas to provide the ion, which is AR gas. Kita akan energize the AR plus, and then vacuum to generate the vacuum level, 10-5, -6, whatever. Power supply to create a large voltage drop between electrodes so that you can create plasma. Right, creation of plasma depends on the voltage drop between your electrodes in the system. Okay, target material is the sputter target to be deposited: silver, aluminium, ITO, zeolite, blah blah. So this is what you get to see through the glass window. Okay, any plasma, can see purple color, very bright purple color in this condition. So any plasma, the very same thing, but you get to see only through the glass window. Not too long, jangan tengok. Kalau you buka tengok plasma, jangan tengok lama, tengok. That's it. Just to confirm the presence of plasma. That's it. Not for you to enjoy. Oh, macam aurora ke apa kan? It's not like aurora. This one is like very intense, bright plasma right in front of your eyes, like 5-10 cm. So it's not good. Mixture of neutral atoms, molecule, roughly equal number of positive and negative positive ion free electrons in a quasi-neutral state. This is plasma. So argon is usually used as sputtering gas because of its chemical inertia to the target material. So kenapa kita pakai argon? What do you think? This is one thing, but kenapa kita pakai argon? Because it's inert, right? What if you use some other gas that is not inert? Like my last question before we stop the class. Kalau you pakai gas, bukan gas lain yang bukan inert, what's going to happen to the process?
Nanti ada reaction dengan target.
As a result, you will get okay, there will be reaction,
apa
yes.
tu?
So bila ada
tapi-
reaction, so what do you get then?
Tak ada yield, tapi nanti dia akan gas tu akan melekat
Gas.
dekat target.
Gas tu either melekat kat target ataupun mungkin done juga. Dan deposited layer tu ada gas tu. Sebab dia tak inert kan. So you're gonna incorporate the atoms from the gas yang bukan inert into the deposited layer. Bila you buat EDX kat SEM, tengok ada gas ni. Dalam layer tu bila you scan. Rupanya dia tak inert. So you don't want to start with that, of course. Cumanya just to make sure that you understand, you use inert so that it doesn't react, it doesn't involve in the reaction with the whole environment, so that the gas is not in the layer ataupun cross-contaminate the target material itself. After all, you want to maintain the deposited layer, and you also need to maintain the purity of target material so that you can use it next time. Okay, so that's the very basic thing of the inert gas requirement. So let's just stop here. We'll talk about plasma formation and the rest of the stuff in the next class. Something like this, Ni gambar dia, ni kalau lab scale on the left, lab scale kecil je kan. Kita punya sistem yang Izati dengan Akilah guna pretty much like this, a bit smaller than this. Lagi like that, I think, about that. Yang belah kanan ni yang Fuji Electric punya. Ni memang the real image yang saya ambil dalam lab. This is the intervac that I talk about. Intervac system. You can see dia punya wire. You can see the chamber there. 2 stack chamber, serial, side by side, 20 chamber all together. Satu chamber sepatah satu layer. Then next. Lepas dia turun. I couldn't remember the flow. I think it start from the top, then habis kat ujung. The final one will be CVD of carbon. So 20 chambers, big one. Then you have to, kalau you nak buat maintenance, you have to pijak atas tangga ni. Then you'll be something like that, right? You buat maintenance, buat cabling kat atas ni. So we need to step up. You tak boleh sampai atas kalau ni sebab it's too high. So you'll be like that. Kepala situ, ini kaki, pijak tangga. You do the PM, preventive maintenance, right? The real system, industrial scale, sputtering. So the one that we talk just now is only this one chamber je. Satu ni je. And if you talk about industry, you have like 20 of those. Different layers, different plasma, different everything. Process parameters. Okay, so that's all for today. Any question for now, sputtering? Can you follow so far? Is it okay? Okay, I'm going to give you your assignment 2 coming probably today or early next week. You need to finish that in 2 weeks' time. Sekarang week 11 kan? We have like altogether 16. 16 will be the revision week. We're supposed to have 3 weeks of lab session in this course. We're supposed to have 3 weeks lab session, and that's supposed to be 12, 13, 14. Sepatutnya, you masuk lab, you run the system, you'll be assigned to one process. For example, that will be group-based. For example, one group is assigned to do oxidation. One group will be assigned to do sputtering. One group will be assigned to do etching, for example. So every group akan buat different process. You don't get to do everything because everything takes too long. And you'll be given like 3 weeks. But it's not happening. Cuma saya nak explain kat you kalau it's not happening because it's pandemic, right? And you're all at home and you're not around. Tapi bila previous batch, 2 batch, Joanna, sorry for that. Before the pandemic, sorry as well, Arisha, I saw you crying. Sebelum pandemic, this will be your presentation for your assignment. Okay, so you're given like 3 weeks altogether, 3 weeks plus, or 3 weeks altogether, 3 weeks. So you'll be divided into groups. Each group will get to do one process. Sputtering, etching, oxidation, blah blah. Mungkin sama proses tapi different material. And at the end of in week number 3, katalah 12, 13, 14 contoh, then week number 14, you have to do group presentation of your process and also on your characterization results. Macam FYP, but then in group, just one process. Contoh kalau you buat oxidation, then you'll probably be assigned to do wet oxidation with certain parameters on 100 or 1, for example. and then you need to do the measurement of your oxide thickness on the microscope, characterization as your visual inspection, compile the data, present as in operation meeting, factory operation meeting, and I'll be the CEO, something like that. Then I'll ask you on the data uniformity, defects. Saya akan set you up macam operation punya ni lah. You are the engineers in charge of that particular process. You presenting your litho, your etch, whatever. What did you get? What did you measure? Do you see anything weird? Or what went wrong? What did you do? How did you plan your parameters? Why did you choose those parameters? So I'll treat you as engineers rather than funny student. So I'll ask you all the tough, mean questions so that you are, okay, this is like being in operation meeting or department meeting. But too bad it's pandemic. Too bad it's pandemic. So you don't get to do the experiments and presentation, but you'll still be doing group presentation, but the content will need to be changed sebab tak boleh buat eksperimen kan. I'll tell you later, perhaps next week. Each group will be assigned on presenting fabrication processes involved in different semiconductor devices. So one group will get to do SSD fabrication flow. Sekarang dalam course ni kan kita belajar IC kan, integrated circuit. So you know the flow of IC, MOSFET, all the stuff. But then you don't know the SSD punya layering, right? Layer condition, the device configuration. You don't know the solar cells, cadmium telluride. You don't know the BJT. You don't know the IGBT. You don't know the GaN devices. You don't know the LEDs. Kita guna proses yang sama, litho, etching, but then how do you use it to form what sort of layers in your final devices? So those will be your presentation. Maknanya nanti saya akan assign you into group. Then you'll need to figure out what are the processes involved for you to fabricate, say, GaN power devices, gallium nitride power devices, or BJT, bipolar junction transistors, ataupun something yang bukan MOSFET lah, ataupun cadmium telluride lah, solar cell, ataupun some other semiconductor devices yang you kena pakai the same process but then different devices. So bila you present, then each will be sharing different process flow for different devices. Then kita akan letak everything on either on E-learn or perhaps Padlet macam dulu. Then bila you nak go for interview later on, kalau you nak pergi SSD, then you just watch the SSD process flow. You nak pergi Infineon, you can see GaN power devices or silicon carbide. You nak pergi First Solar, for example, then you can go and watch cadmium telluride process flow and so on and so forth. So then eventually everything will be ready on a platform that you can refer later on. Okay, selagi mana platform tu masih ada, Padlet tu masih ada, for example, then you can always refer for your job or internship later on. So yeah, the previous condition was they ran experiment, characterized, get the data, compile data, present, and I'll just be a bad guy in the presentation. Okay, so for this particular time, due to pandemic, macam last batch juga, so it will be more on the process flow kind of study, and then you compile, you explain, and I'll ask you as a bad guy as well, what did you do? Why do you do this? Why do you choose certain parameters? How do you combine all the different processes? But the mindset of the presentation will be mindset of engineers presenting process flow. Okay, so that you are prepared of what is it like to be in the real world there. I bet you will appreciate the session because I won't be a good guy. Right, so any question, Stuaf? There? Right then, if there's no question, then that's it for today. I'll see you next week. Inshallah, bye-bye. Take care. Assalamualaikum.